doing section 3-4. It's called lines in motion. Let's put all the phones away, take the headphones off, and get ready to jump in. Now today is kind of an introductory lesson for what we're going to do over the next 4 days. So we're going to do today, we're going to cover a whole bunch of stuff, and it's going to seem like it's a lot, but don't get overwhelmed, because then what we're going to do is we're going to break it apart over the next 4 days and spend a whole day on each part and like really dive deep into it. Today is just to get you get your feet wet with everything. So we're going to touch on everything, and then we'll spend a whole bunch of time like really getting to make sure we understand everything well. So there are 2 main goals. First goal is to start learning what transformations are. Second goal is to get introduced to some families of functions. All right, so I'm going to walk, instead of going on Desmos, which we did in third, but that's okay. We're just going to talk through these a little bit. So suppose we have the line f of x equals 2x, or y equals 2x. So what's the slope of that line? 2. What's the y-intercept? 0. If I wanted that same line, same slope, but I want to move it up 3 places, what equation could I use that will give me the same line shifted up 3 places? Very good. 2x plus 3. So what I want you to do, instead of just thinking of this 3 as being the y-intercept, here's what I want you to think of it as. This 2x, that's our function, right? So like if I plug in, into this function, what would f of 1 be? 2. What would f of 2 be? 4. F of 3? 6, right? Okay. All of those values you just named, those are output values. They're y values, right? If I take all of my y values and add 3 to them, I'm taking every output and adding 3 more to it. So it's not just a y-intercept change. You're changing every single y value on the line by adding 3 to it. So you're shifting the whole line up 3 places. Okay, so that's just an intro of what we're doing. So if we had to shift down 4, we would have 2x minus 4. Very good, because now we're going to subtract 4 from all the y values. So vertical shifts up and down, they're also called translations. Vertical translations, those are easy. You add to the y, you subtract from the y, life is good. To move the line left or right, let me say this. If I take a function and want to move it up or down, I add or subtract from the y. But if I want to move it left or right, I got to add or subtract from what? The x. And it works kind of opposite from how you think. So if I want to shift to the right 3, I am going to take my x and subtract 3 from it. So you kind of do the opposite, bless you, of what you think you would do. And if had time, you know what, I'm going to take Desmos for just a second. You guys don't have to, let's all watch together. So, okay. All right, so if we graph y equals 2x, and then I graph y equals 2 parenthesis, now I've already forgotten it. Let's see, x minus 3. So this is, the red line's my original line. The blue line is my new line. So even though we're subtracting from the x, we're actually moving our line to the right. So it's kind of weird. When you do a left or right shift, it does the opposite of what you think. The sign is always opposite. Left is plus, right is minus. So anyway. All right. So knowing that, in your groups, I'm going to give 30 seconds to see if you can come up with an equation that would take 2x, this line, shift it to the left one place and up 2 places. Discuss it for a minute in your groups. All right, so Bhuvan, what did your group come up with?
We got 2 parentheses x minus 1 or x plus 1.
Ooh, okay.
And then plus 2.
Did anyone else get the same answer? Yes, well done, and that's correct. So here's what happens. To go left 1, you're going to add 1 to the x. And then to go up 2, you're going to add 2 to the y. So y goes normal. Up is positive, down is negative. X is opposite. So if we had to shift to HK, this new point HK, you would do x minus h and then plus k. You're going to see the letters HK get used a lot over the next, years. All right. Does everyone have this down? This was just our intro page. Quick, let's just see if you picked up on this. Doesn't have to be a line. We have this funky piecewise function here. The original function is in black. The new function, the translated function, is in red. So if the original function in black is y equals f of x, what did they do to create the red function? Shifted down 2, subtracted 2 from the y. I love it. All those answers are correct. So yes, so our new equation would be f of x, whatever that is, minus 2. Just bringing it down 2. How's that? Is that okay? All right. So that's done. Okay. I'm gonna introduce you to some new function families. We're gonna start with the quadratic function family. All we're gonna look at today, don't even worry about this. All we're gonna look at today is f of x equals x squared. And what I'd like you to do is take a minute and create a quick table, an xy table for y equals x squared. So if x is negative 2, think about what f of negative 2 would be. So take a minute, create a quick xy table, and then get ready to sketch some graphs. They can just be on paper. You don't have to have graphs. Once you have your table done, check your answers with your group mates. Make sure that you all agree. All right, what is negative 2 squared? 4. What's negative 1 squared? What's 0 squared? 0. What's 1 squared? What's 2 squared? 4. All right. So if I like that, it's a palindrome. You know, that is actually a really nice way to think of what's called y-axis symmetry. So, okay, negative 2, 4, 2, 4. So if we graph those 5 dots and connect the dots, we get this kind of a U shape. Not perfect, but you know. All right, we get this kind of a U shape. Does anyone know what this shape is called? It's called a parabola. And we are going to study parabolas not just in this unit, but later on in another unit. We go kind of in depth. So anyway, but parabolas, there's something really special about parabolas that you may not know. Parabolas have a thing. This is really bugging me. There we go. That's a little better. Have a point that's like somewhere around here, and that point is called the focus. And what happens is anything that gets sent into the parabola, no matter where it hits, even if it hits like way up here. So if we have something that comes along and hits the parabola, it automatically bounces off and gets sent to the focus. So it doesn't matter where it comes and hits, even if it hits down here, it's going to reflect off and get sent to the focus, right? So wherever you have a line coming in, it goes to the focus. Now, why is this important? Because if you've ever seen, now they're not as common as they used to be. They're common in space, but they're not as common on houses. When I was, like, say in like the 80s or 90s, there used to be satellite dishes on a lot of houses. Now, there's still some? Okay. So if you've ever looked at a satellite dish, did you ever notice when you look at the dish that there's like an arm thing that is kind of positioned like over the dish? It's called the receiver, right? So all satellite dishes have to be parabolic. They have to be, the shape has to be a parabola. And then that receiver is positioned at the focus, right? So that any signal that comes in and hits the parabola gets automatically directed to the focus. And then the focus, which is that receiver, is usually hardwired into your house or whatever it's going to, right? So you get your TV signal, right? And then the reverse, which also, these are all kind of old examples. I'm showing my age a little bit. So old flashlights. If you've ever had an old flashlight, not one of like the big fancy with 48 LED lights inside, but like just one bulb. So if you've ever seen anyone ever taken apart an old flashlight? Okay, Avi. So do you know what I'm talking about when I say like this metal curvy dish in there? Yeah. So there's like a metal curvy dish in the flashlight, and the light bulb, believe it or not, is positioned at the focus, so that what happens is if your light, which is here, goes out and hits the parabolic dish, it gets projected out in a straight beam, right? And so that's why they put that dish in there, is so that the light just doesn't disperse. You get like a beam of flashlight, and it's that parabola that does it, right? Yay, parabolas. Okay. So anyway, all right, that's enough about parabolas. Moving on. Absolute value. Everyone take a minute, and I want you to build a table, not for this guy, just for this guy, for y equals absolute value of x. Y equals absolute value of x. Okay. You guys need another minute, right? What's the absolute value of negative 2? 2. What about negative 1? 0? 1? 2? Okay. If we are to plot these points, negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. We actually, you'd think it because, you know, it kind of looks like it could be, but this is actually a V. Those end up being lines. Now, not all absolute value functions are lines, but all the ones that we're going to do in this class will be lines. So we end up with this line, these two lines called a V shape. Really, this V shape is actually just two lines put together. So this line on the right, that's y equals x, slope of 1, coming out this way. This line on the left is y equals negative x. So if we take y equals negative x and do what's called restricting its domain, so we go negative infinity to 0 on y equals negative x, and then 0 to infinity on y equals x, put them together, and we get absolute value of x. Any absolute value function can be broken down into non-absolute value functions and just pieced together. That's called a piecewise function. And the fun part is in calculus, you never get to use an absolute value function every single time you get one. You have to break it into a piecewise. It's the only way to work with it. So we're going to do some of that later on in this unit. So breaking absolute value into piecewise will be fun. Hey, let's just review for a second. What's the domain of this graph? Fantastic. All right, did you guys all hear that? Domain, is that x values or y values? It's the x values. Every x value where you've got a dot on the graph, right? Okay, so negative 3 to infinity, or you could write all real numbers, right? Okay, let's see if you really know what you're doing. 0 to infinity, right? Okay, very good. Range is lowest y value to highest y value. Do we include, first of all, do we ever include infinity? No, you can't include infinity. It's like it runs free. What about 0? Yes, there's a point at 0, so you bracket the 0 to show we include the 0. All right, we'll do more practice with that later. That's not okay. Square roots. Square roots. So I'd like you to take a minute and fill out this table for y equals the square root of x. How do you know about 2i?
Because I googled it because it was on one of the
Huh. Did you really? Wow. We're just, guys, let's just use real numbers for now. You don't have to put any imaginary. No eyes. No eyes. Don't worry about it. I is the square root of -1. Eyes are the things on your face that you see. Yep. Ruben, what do you call a fish with no eyes? Ruben, are you okay?
I was aiming at the track. Okay. Yeah, right.
Science is not a bad thing.
That is such a serious observation. All right, so quiet please. Jay has a problem with this problem. Okay?
Yeah.
Jay, what is your concern? There's no square root to a negative number, which means this is not in the domain of our function because there's no output associated with it. We're not doing eyes. So there is no answer. So we just, nope, out. What about 0? 0, because 0 times 0 is 0, so the square root of 0 is 0. What about 1? What's the square root of 4? What's the square root of 9? 3. All right, are we all good? Could we do 16? Yeah, okay. All right, so let's plot these points. Wow, it's almost like we knew there weren't going to be negative values. Isn't that crazy? Okay, yes. So 0, 0, 1, 1, 4, 2, 9, 3. So if we connect these dots, what just happened? There we go. Okay. So I have a question. Quiet down, please. If you were to turn your head sideways and pretend that my graph looked good and was not wobbly, what shape does this remind you of? It's an upside down boat or a parabola, right? Okay, so this is a parabola turned sideways. It's only half a parabola, right? Turned sideways. And does it make sense that y equals x squared and y equals the square root of x would be similar shapes, right? Because really, if y equals root x, if I square both sides, this is x equals y squared. which is just y equals x squared. It's technically turned sideways and flipped over, but anyway. Okay, so yeah. So they are related, which means that whenever you're doing a square root function, you're doing a sideways parabola. It's like a, anyway. All right. Moving on. We're going to study 4 types of what are called transformations. And the first type is called translations. Now, I wrote this and it's kind of convoluted. You don't have to write all this today. This is me just trying to kind of explain that when you move to the left, you add to the x, and when you move to the right, you subtract from the x. And when you move up, you add to the y, and when you move down, you subtract from the y. But if you don't want to write that today, it's okay. Not a big deal. Whoa. You want it? Okay, you can write it. It's okay. All right. So we did this with a line earlier, but it doesn't have to be a line. The same method of shifting a function around left, right, up, and down works for every type of function there is. We could do linear, quadratic, polynomial, exponential, logarithmic, trigonometric, right? Inverse trigonometric. We could do hyperbolic, right? All these different functions all use the exact same method for shifting. So I showed you right here this y equals 3x squared. And remember what do we call this kind of a function? It's quadratic, right? So if I change this to 3 times x minus 5 squared minus 7, I'm subtracting 5 from the x, which shifts it to the right by 5. I'm subtracting 7 from the y, which shifts it down by 7. So the squared is just, that's part of your function, right? But the 5, when you do a left or right, it has to be kind of with the x. So you can kind of put the x in parentheses with the shifting. And then the up or down is on the outside. So anyway, all right, so we're going to translate the graph of y equals x squared by moving it 3 units up, or I'm sorry, 3 units left and 1 unit up. 3 units left and 1 unit up. So without the equation, you don't have to do the equation yet. First, let's just start with the graph. So we're going to take this graph, this is y equals x squared, and we're going to shift the whole graph 3 units left and 1 unit up. So you can, if you're doing it on paper, you can do it on the same grid if you want, or you can do it on a new grid. I think, you know what, I think I might actually just do it on the same grid so you can see the new graph. If you're ever stuck, like I just don't know how to start, pick a point, right? So like say I pick 0, 0, and then just walk 1, 2, 3 to the left, 1 up. That's your new point for that, like this is called the vertex of the parabola. That's your new vertex. Did y'all see what I'm saying? Like 3 left, 1 up. Okay, so like this is the point, this point negative 1, 1 right here. So I would take this point and go 1, 2, 3, up 1. And this point right here, 1, 2, 3, up 1. And if you keep going, you end up with a parabola, and the whole parabola has been shifted 3 units left and 1 up. So, question, get this. I lost control of the board. Where's my mouse? Whoa, whoa. All right, there we go. I don't know what this is doing either. Okay. So if the red graph is y equals x squared, and I want to go 3 units left, what would go in these parentheses? X plus 3. And then I went 1 unit up. What would go out here? Plus 1. All right. Okay. That's called a translation. Now we're going to do a reflection. A reflection is when you flip something over an axis. So there are the main types of reflections are reflections over the x-axis and the y-axis. I also included a reflection over the line y equals x, which we'll look at in a minute. All you're doing when you're reflecting is you're changing the sign of everything. If I reflect over the x-axis, means all my y values, like if they're like this, change sign. If I reflect over the x or over the y-axis, then all my x values change sign. So what ends up happening is a y-axis reflection, you multiply all your x's by -1, an x-axis reflection, you multiply all your y's by -1. All right, which we'll get to deeper on our day when we spend the whole day on reflections, right? Right now, I just want to know that you can graph it. We're going to use the root function, and we're going to reflect this. When you're reflecting, you create a mirror image. So if I reflect over the y-axis, I'm going to put my original in red. There's my original root in red. I'm reflecting over the y-axis. I'm going to put my new function in blue. So everyone with your hands, I want you to show me the original and what the new function is going to look like.
Original?
Yep, and the new. Okay, there's the original.
Oh.
Let's see, I don't know if I can do it with my hands.
Oh, wait, over the y?
Yep,
Oh, okay.
something like that. Like that? Okay. So what happens is the y-axis becomes what we call an axis of symmetry. And so it means that you've got the exact same image mirrored on each side. If you were to take this paper and fold it, it would land on top of itself, right? If you fold it along the y-axis. Yes, Joe?
If you go diagonal.
That's what we're going to do in a minute. Don't you worry, it's coming.
Oh,
All right.
Joey went again.
But first, we're going to reflect over the x-axis. So there's our original. There's the x-axis. What would the reflection look like now? Good. All right. I see Grace. Good. All right. Good. Yeah. 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 Very good. Obvious. See it. Good. All right. Fantastic. Something like that. Do you understand, like, does everyone understand what's going on? Michelle, how you doing? Double thumbs up. Okay. Good. All right.
The twin has a question.
The twin.
Yeah.
Can you scroll back up a little bit so I can write down the y-axis?
Thank you.
While Ashwin is writing, your next reflection is going to be over the line y equals x. All right? Okay. So, wait, I draw the original. Okay. There's the original. There's the line y equals x. Perfect, but that's all right. Okay. When I was young and I used to have to do a reflection over the line y equals x, I would take my paper and turn my paper so that y equals x is straight up and down, and it was easier visually for me to see how to reflect it. I can't obviously do that with the smartboard, so I'm just going to turn my head so that I'm looking at this straight up and down. So if this one's going this way, I'm going to do this. It goes like that. Pretend that they're symmetric. Now, one thing I wanted to show you about ordered pairs when you're reflecting, we have 3 minutes. We can do this. Really quickly, if this is the point, so y-axis, if this is the point 1, 1, this is the point negative 1, 1. If this is, we're doing square root 4, 2, negative 4, 2, right? So the x changes sign. if you're reflecting over the x-axis, 1, 1 becomes 1, negative 1. The y changes sign. But if you're reflecting over the line y equals x, 1, 1 stays 1, 1. But if, pretend this is such a bad graph. But anyway, pretend this is 4, 2. 4, 2 now becomes 2, 4. So 9, 3 is now 3, 9. Why? Because when you reflect over y equals x, your y's become x's and your x's become y's. Right? All of your variables swap. All right, last one. What kind of a line is y equals 1? It is horizontal. What's going to happen? Exactly. They're going to crisscross, right? All right, there's one more thing we got to do before time's up, and I still have to hand out your homework, and that's rotations. Oh, God, we have to do dilations. All right, we're going to go so fast. Are you ready? Don't write this down. I'm not even going to let you. Okay, when you dilate means stretching or shrinking. Stretching or shrinking. So if I have to dilate in all directions, because you can just do X and make it wide, or you can just do Y and make it tall, but if we're doing all directions, all you do is multiply everything. Here we're going by 2. So the point 1, 1 now becomes 2, 2. And negative 1, 1 becomes negative 2, 2. This circle had a radius of 2. What's my new radius? 4. 4. 4. 4. 4. 4. Let's see. I'm terrible at circles. Okay. And then my smile goes out, doubles, doubles. And there's my dilated figure. Okay, last thing. I've got you for 60 more seconds. And you have to get homework. Don't leave without homework. A rotation. Shh. If I have to rotate 90 degrees about the origin, you stick a pin in the origin and you turn it. A rotation is a turn. So if I'm going to rotate this, here's my origin, my new graph. Is if I took this and turned it. Does that make sense for rotation? All right, that's it for the lesson. Wait, let me give you homework. Let me pause this.